Hi everybody, this is Mr. Folly, and welcome to our key, of worksheet 3.1 for intermolecular forces for AP chemistry. Which is expected to have the greatest dipole moment? In each case, justify your answer. So, C to N or C to F. So I'm considering in the periodic table, notice carbon's the same. I have N and F over here. So C to F. So F is more polar, more electronegative, because it is smaller and has more attractive protons. So the change in electronegativity, delta En, is larger for C to F than, notice it's not than C to N. Okay, so it's a different in electronegativity. Good. So then I have N to P, and N to P, and N to SB. And I look over my little shoulder at my periodic table. Oh, I'm not even going to do that. I have a periodic table right here. How great is that? I hope yours is just as handy. So P and SB. So P is on top, right? On top. Okay. So remember what we're going to have here. So nitrogen's kind of a constant, and nitrogen's going to be more negative. Nitrogen is more, I'm going to say, electronegative. So didn't have a question from somebody, sorry. So nitrogen is more electronegative. So that means SB is least electronegative because it has more what do you call those energy levels. So it is larger and attracts. Oh, let's see if I can erase the stuff I had in here. Hey, I can. Attracts electrons worse. The change in electronegativity is bigger for N to SB. I just want to make sure I had that clearly labeled. Okay. All right. According to Coulomb's law, does the force of attraction increase, decrease, remain the same as the size of the charge difference increases? The size of the charge difference increases. So Coulomb's law is bond energy equals, and I'm ignoring of stuff, Q1, Q2 over radius squared. So if the force of attraction increase, decreases the size of the charge difference. So that would mean I had 1 times -1, or 1 times -2, or 1 times, I'm sorry, I didn't mean to do 1. Let's do 2 times -2, or 2 times -2, right? So in this case, clearly, when the difference becomes larger, right, bond energy would be bigger. Okay. Between the distance. Yeah. Explain your answer. So, algebraically, if Q's increase, I write Coulomb's law. Algebraically, if Q's increase, then bond strength, or bond energy, I suppose I should call it energy because it's BE. Then bond energy also increases. God bless the algebraically. Yay! Okay, so this is my rationale for it. But really, if you write this down and you realize they're talking about Q's increasing, you're going to have it. All right, look at the pretty colors. Oh, I don't know why this is kind of dodecahedron-y, but that's okay. The image above is the electron density of HF. Is the molecule polar or nonpolar? Oh, let's see if we can get a good squint in here. Okay, so this is a big atom, and this is a small atom. So that means this is H, and this is F, right? So is the molecule above polar or nonpolar? So this is the electron density. So this is high density, high density, and this is low density. Okay, so is the molecule polar or nonpolar? Polar, because electron density, now I have to justify it, so I have to refer to this, because electron density is not consistent across the molecule. To the left and right of the molecule, label one side delta positive, and the other side delta negative. Okay, so delta negative, delta negative, and delta positive. It says justify by referring to the electron density. Okay, so F is delta negative because it has a greater electron density and electrons are negative. Okay, there you go. How does a neutral particle like HF gain a partial positive and a partial negative? The atoms attract electrons differently. Differently based upon my two favorite things for trends: size and nuclear attraction. Nuclear attraction. Good. What's the difference between a single bond, intramolecular force, and intermolecular forces? Single is 100%, is much stronger. Remember, typically it's about 10 times stronger, right? Electrons are shared by two atoms. Inter has attractions between two molecules, not atoms. So the difference would be the strength, and the difference is whether it's a molecule or an atom. Okay. London dispersion forces form. Explain how. Include a picture. So I got myself a little boop, and I've got, say, 5 and 5. Neighbor 5 and 5. And then by chance, my electrons are going choo 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 choo, and by chance, I get, I'm just going to make this go all the way across, I might have 6 and 4. This side's a little bit positive. Because this side's a little bit positive, choo 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 choo, these electrons now are going to love that, and I might get 7 and 3. So this one's going to be a little bit negative, and they're going to do that. Okay, so now I have to describe that. Two neutral atoms are near each other. Electron motion, because remember they move around their clouds, creates an imbalance. Oops, I put imbalance and misspelled it. An imbalance and a slight charge. That the neighbor atom, I call them atoms. They don't have to be atoms. Let's call them particles. They don't have to be atoms. They're probably molecules. Are near each other because an imbalanced slight charge that the neighbor, won't you be my neighbor, particle responds to by shifting electrons in its cloud, and positives and negatives attract. Sweet. All right, I had my quick pause. Now I'm back. So if I have HF, which in our picture above we saw was delta positive and delta negative, and I have another HF, which is a delta positive and a delta negative, and then, so I'm including a picture, okay? So two polar molecules orient themselves so the positive end is closest to the negative end, and dipole forms. Explain how hydrogen bonds form. Include a picture. Okay, so we'll do water. H, boom, 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 and another H. You remember how I like to circle my molecules because it emphasizes the difference between a molecule and an intermolecular force. Here's H, O, H. Whee! Okay, so the oxygen and the electrons are particularly negative. The hydrogens are positive. Delta positive, delta negative, delta positive. Okay, there's really two delta negatives here if you want to get all picky about it. But then we get this, that interaction right there. Explain how hydrogen bonds form. Include a picture. Two molecules. Oh man, I'm gonna change that to one molecule. This is a hydrogen bonded thing to a hydrogen bonded thing. So, one particle with H directly bonded to very negative, very electronegative N, O, or F is attracted to the lone pair on a different particle. All right, good. All right, so here we go to sign a field trip form. How dipole, induced dipole forms. Okay, so positive, negative, and then I've got a neutral. And I put that in there to neutral. See this negative sign? Oh no, I'm going to repel the electron cloud. Well, I'm gonna redraw this and make it big enough for everybody to see. Okay, so here's my positive, my negative end, and here's my neutral dude. I'll put it right down the middle to be neutral. So this negative side repels electrons. So that means the electrons in here, so say this was 5 and 5, what happens is it turns into 3 and 7. Oh, let's see how well I can do. Okay, so this end is now delta positive, and this was my negative end and my polarity end. Okay? So, and these would be deltas too because they're polar, they're not ionic. But so then it's a little bit of an imbalance. Okay, so now let's go to explain how dipole-induced dipole forces form. Picture a polar molecule's charged end causes, and another word for causes is induced. Oh my goodness gracious, now I get it. Causes, oops, I put it induced. Induces the neutral neighbor. Uh-oh, I hear some evil going on in the music over there. Electron cloud, whoops, to become slightly positive and negative to form a dipole induced dipole. Notice I called it a force instead of a bond. I think bonds are intramolecular and intermolecular forces. They're weaker, so that's how I do it. Ion dipole forces form. Oh, it's so much. It's the same all over the place. Do I still have to include a picture? Yes, positive. So I've got a positive thing right here, and I start with neutral ones 5 and 5. And what happens is, because this is positive, the electrons love it. So positive. And my neutral dude, now because it's positive, is going to be 9 and 1, right? And that's a, woo, look at that strength of that one. Okay? So, an ion's attraction. Oh, I did the wrong thing. I thought it was an ion-induced one. Oh, man, I did it wrong. Ion dipole. So here's a big Mac Daddy positive, and I'm going to have back to my, woo, positive, negative, and it's delta positive, delta negative. So a full ion attracts the oppositely charged molecule. Molecule end. Here we go. To form an ion dipole force. And again, I like forces for intermolecular forces. It indicates that they're weaker and are usually shown as dashed lines or just polarizability. Larger electron clouds allow more electron arrangements and makes temporary charged sides more common, likely and common. So bigger makes you more polarizable. More surface area does that too, but I don't see that too much with surface area. Explain how polarizability increases and increase the number of electrons. More electrons equals bigger cloud equals more ways for uneven distribution. Electron distribution. So now polarizability increases with an increase in surface area of a molecule. Oh man. More surface area. Equals more ways. So a bigger surface area, that means you've got more ways to arrange to have uneven electron distribution. All right, I'll pick up again on number 9, the end of part 1. Toodles.